The final talk of the workshop and indeed of the programme. It's a very great pleasure to welcome a dear friend to our maths and energy activities in the UK, Sean Meyn, who'll be speaking on resource allocation for demand dispatch, state space collapse and market applications.
Great, thank you. Oh yeah, so it's been almost exactly 9 years ago that we had the Energy Systems Week, and I don't know if you remember, but David and I had Sherry the night before the week and discussed talking about the energy grid in 2020 and all the issues, and it was quite an experience. I mean, God, there's some debates there that were wild. And one thing I remember is that back then, I remember several people, old-timers in power, sort of warning us newcomers. I'd only been in the area for like 5 years. It's not a communication network, you arrogant, pricks. You're coming here with all your tools and your whatever, and it doesn't. This is there are there's reactive power and blah blah blah. It's just and there was a bit of defensiveness 10 years ago, and then 3 years ago, I guess, Frank and I were in Irvine at some sort of mathematics of energy systems meeting, and I mean you led the discussion. You said it's actually a lot more like communication networks than we thought, and I think that more and more, that of course when you get down to time scales of seconds, you've got a lot of things to worry about, but when you go to the kind of slower time scales that I can talk about here, that's it's not that different than a communication network. And so anyway, that's this one thing here. This term state space collapse, I'll explain, it comes from the queuing theory community, and in particular work by Frank Kelly some years ago. So this is joint work mainly. Most of this work today is with my graduate student Joel Matthias, but it's based on prior work with Anna Busic, who's here somewhere, and my student Neil Kamadela, and Robert Moy, who's an executive. He's my age, but he's trying to get a PhD in his spare time, and he's been involved in this as well. And we're working with this sweet little company called what is it? Electric Power Engineers in Austin, Texas, who might be able to help us with this, besides NSF, DOE, and RPE. Okay, so, whoa, slow down. Oh, talk's over. What happened? Oh, all the jokes have been given away now. Okay, so I know most of you weren't here in January, but still I'm going to go a crash course through what I was talking about in January, because I need to say it. I mean, so our goals have basically been trying to make a bunch of loads look like a battery, charge and discharge. And Anna Busic gave a great overview of it all yesterday. And this is a cartoon from her talk, and just to emphasize the idea that we'd like to provide these services while making the consumer happy and the appliance happy, but supply the resources needed. And a water heater is such an obvious resource because it's a storage device. It's storing hot water, so it's just thermal energy storage instead of electric. And this is a quick thing just to say we want to do everything. We want to do like AGC, what is called the balancing reserves in the Pacific Northwest. We want to do peak shaving, these awful peaks in New York every afternoon. We would just like to flatten them, And we could. I mean, it's all buildings. It's giant buildings, thermal energy storage everywhere. Some pre-cooling. We could just knock it out. Just let us in the room, And we'd like to be able to flatten out these duck curves people talk about. And also deal with contingencies, although this scares me a bit. Like I said, when we get to second time scales, I don't know as much, and I don't want to say I have any answers at all. It's the other things I think, we could really make big impact if somebody would let us, Okay, and it was amazing last year when I was at the Simons Institute. It was Stephen at a program that Stephen helped organize. They had the record duck curve in all time shown here, where this yellow part is the renewable energy from solar energy, and there was a record in terms of the amount of solar energy and a record in terms of the ramps it created. I don't need to go through this, but they needed 10 gigawatts of thermal generation for just a few hours. They had to throw away a lot of the energy. There was just no way. You can't just suddenly turn on all these power plants. So you just throwing away energy is the biggest resource they have. So So basically, the duck is this thing in red. You know, people have been told that's a duck, and now we all believe it's a duck. Okay, and the goal, you know, is to flatten that duck. We want us to squish it. And I know we can. You know, and they're planning to electrify California. They'll install all these electric water heaters. There's big fishing industry, all this refrigeration, all the supermarkets. And Florida's even better because everyone's got their air conditioning in full blast, and that's thermal storage. And you can, Disney World could probably regulate all of Florida if you could just educate the policymakers. You know, so that's the goals of our research. We want to be able to implement this. I think a lot of the science is done. You know, the policy issues are the biggest. Yeah. Florida, the thing is that I'm going to say at the end, I don't see anything wrong with vertically integrated duopolies. I think they're good. All right, that's my punchline, you know. But I don't like Florida governments typically. And you know, so there's, you know, basically our previous governor, you know, is a climate change denier, and you know, and if he pushed for solar energy, he wouldn't get money from the Koch brothers to finance his Senate campaign. You know, so it's like the politics are horrible. You know, it's really awful in Florida. I'm being recorded, aren't I? Oh well. Now, you know, if you showed this plot to anybody in the world, they would not know what you're talking about. If you ask them, what does a water heater do? And they could guess the temperature does this, that it goes up to 120 degrees, say, and then cools down to 110. But if you told them that there's a spike train of 3 kilowatts and then nothing happens for 5 hours, and 3 kilowatts and nothing happens for 5 hours, they would go, oh, I guess so, you know. But the fact that nobody even knows what their power consumption looks like is a hint, you know, what I'm saying, what I said back in January. They don't know anything about power. They don't know that it's a spike train. They couldn't care less. And that is a gift to a control engineer. The fact that they're oblivious to the thing that the grid operator cares about. You take those, can you see, this is an example where we have 100,000 water heaters. Anna went through this. And I changed the color scheme for people who have trouble with, the yellow wasn't good. You know? So the red is when it's on. This is one of the 100,000 water heaters. This is when the 100,000 water heaters are not trying to help the grid at all. They're just acting normally. And then repeat the simulation with the same seeds, the same random number generators. And this guy is now helping to provide this maximum regulation signal for the grid, right? Yeah, I challenge you to see which is which, you know. Maybe I played a trick on you and I flipped these. You just can't tell. There's no way to tell. It's the fact that, so water heaters are awesome because the fact that there's spike trains, you just move them around a little bit and you can do this. And this was purely with distributed control. You just basically broadcasting a regulation signal, or the signal zeta, the mysterious signal that was given yesterday. And so you can do this. So that's this fantastic mismatch I talked about. All right. So the idea then is to somehow, alongside traditional resources like flywheels and batteries and generation, be able to put flexible loads in the loop and maybe have feedback like Anna talked about yesterday. Maybe the balancing authority has to measure the aggregate power consumption from all the water heaters. I actually challenge that. I don't think we need that at all. I mean, generators provide services today and they're lousy at it. There's a 25% error and the grid doesn't blow up. We don't need this accurate tracking. If we want perfect tracking, we need feedback, you know. But today the grid doesn't blow up, even though the AGC provided by generators is off by 25%, you know. And it's because the feedback loop using frequency compensates for that error. You know, so I think we can get away without that and just measure phase, voltage, frequency. The only thing the balancing authority has to know is the state of charge of the devices. Do I have a resource available? That's what's really critical. The rest, I don't think so. All right. So then you know, this is a blindingly fast recap of an hour-long lecture in January. Then you come to the way people typically think about economics, and they want to put it in a competitive equilibrium model. And there's so many reasons why that model is flawed in energy. And one of them goes back to work that I did with Nkut Cho in my very first paper 15 years ago, where you look at this competitive equilibrium model. You have welfare functions for the supplier, the generators, and one for the consumers. And a market's efficient if these separate optimization problems lead to the same answer. And the Lagrange multipliers give you a solution to that. So basically, there's a Lagrange multiplier for supply equals demand. That would be the competitive equilibrium price. Now, what I said is that if you look at the welfare function for the supplier that's typically used, there's a cost for producing power. Typically it's very linear. And then there's the price times power, which is my income rate. But for the consumer, having a welfare of power is ludicrous. And it's ludicrous almost always. There are examples where it's not true. I mean, if you've got if you've got this aluminum plant going and somebody pulls a plug, you blow up your inventory. That's bad. But maybe 50% of energy consumption is very deferrable, and so having that as a model is going to give you answers that just don't mean anything. Okay, so given this picture, the value of power to consumer is meaningless. That's true for residential home. It's true of hot water heaters, for heating and ventilation, for refrigeration. It's just the lights, which are LED, and what else? I mean, the computer, it has a battery. You can unplug it for a while, a couple hours. Everything's deferrable. So anyway, so this value of power is what I was criticizing back on Saturday. And so what I'm going to do in today's lecture is to build on this a bit. And what if you build an economic theory taking what people really care about, which is the blue curve versus the red curve? And I'm going to give you an answer. And then I'm going to make fun of myself again. Because I don't believe in this stuff. I don't believe in competitive equilibrium theory. I really don't. I believe in markets, but I think competitive equilibrium theory is deeply flawed in most contexts. And I hope that can be a discussion during the panel. I really, and I'll try to make my case for that. So I'm going to talk about optimal control and talk about what the market outcomes would be if I believed that was the way to think about this. If you took truly rational agents, take into account what they really care about. Okay. All right. So here's a big list. So I gave a recap. I'm going to tell you what the social planners problem is, which is an optimal control problem. The definition of efficiency is that you achieve the social planners problem, optimal control problem. So I have to tell you what that is. And it leads to this pretty state space collapse, just as you find in communication and queuing networks. I was inspired. I mean, I wrote a book based on inspiration partly from Neil Law's thesis with Frank Kelly, and also work by Mike Harrison on state space collapse, and it magically appears here. I think it appears in power in a lot of cases. So I think what I'm saying won't be that new to some people. And then I'll tell you what the prices would look like in this equilibrium, and they're fascinating. But I want to talk about the real conclusions then. And I think I got lots of time to do this. It's not a lot of material. So I'll just give you a picture show. So first, let's look at this control problem and how to solve it. All right. So basically, we want to solve this problem, flattening the duck curve. And so we want to minimize the cost of supplying the forecast net load. So we're going to look at like an MPC type problem. And we're going to have generation and the energy and ramping each come with a cost. And so we're going to model that as some convex cost on generation, its derivative, which I think is reasonable. And then we're going to have something reasonable for loads, not a utility function of power, but a utility function for what they care about. For air conditioning, refrigeration, water heating, irrigation, pool pumps, just the filtration systems in pool pumps. It's a gigawatt max load in Florida and California. And then solve this optimal control problem. All right. Now, there's a state of charge surrogate for loads just like a battery. And if you think about it, it's just like for hot water, it's like the temperature of the unit, And so it's the amount of energy, but not electrical energy, but thermal energy. But for pool pumps, what's the state of charge? It's like, how much cleaning have I done? And we'll model that as a linear model. We'll look at like a discounted, a approximation of the amount of cleaning over the last 24 hours, something like that. Okay. Okay, so we're going to take a leaky battery model that was first introduced in Berkeley for TCLs and by Anna Vucic and I and our students at, for like irrigation of pool pumps and things like that in Florida around the same time. And you'll see this notation minus UI, I hate it. That's the deviation of average power consumption from the nominal. If you don't like deviation, you could just take it to be actual average power. The minus sign is that I want to treat the loads like batteries. So if U is positive, I'm supplying power to the grid, and if it's negative, I'm withdrawing energy. I want all the units to be the same. So there's this funky minus sign right there. And again, X is going to be the state of charge. Again, for water heaters, it would be proportional to the deviation of average temperature from the nominal. And so the model for that, a typical model, the simplest model for TCLs, is a linear model like that. And we're adopting the same thing for like pool pumps, for cleaning, how many cleaning hours. And we have a lot of justification for that. It's a bit strange, but we'll take it for granted in this talk. And again, I've said this, but again, first of all, this is the average water temperature, not for one water heater, but the average over the entire population, right? So when it reaches its maximum, it means all the hot water heaters are at the max temperature. When it's at minimum, they're all at the minimum temperature. So it does represent the normalized energy storage at time t for the class I. I could represent water heaters or refrigeration. But secondly, through studies both at Berkeley and at Florida and INRIA, we found that if you respect quality of service constraints, if you take this model and you respect the quality SOC constraints, we found empirically that we can track signals that satisfy those constraints. So as long as the temperature remains in bounds for the average temperature of the population, we find that when we really reach the limits, we find we get too much cycling. So that becomes a problem, but that's all. So, but we have a million papers here, and we can almost reach the capacity limits that state of charge would impose. If you know what I mean. Just look at the average of the population. Right. Okay, and so then you end up with this finite horizon optimal control problem, where you have a cost on the state of charge. So we're relaxing hard constraints on temperature by a convex function. It could be 0 and then blow up very fast. So no hard constraints here. That's important. And then a cost on the derivative generation, a cost of generation. And if we had many generators, we'd have to have a sum of the generators. So that's life. And an important fact is that we're going to assume that the costs on the state of charge is separable. It's a sum of costs. Right? We're just looking at, in numerical examples, there'll be 5 different load classes, different kinds of water heaters, refrigeration, et cetera. Good. All right. So here is the way we're going to set this up. We want to minimize this integral of costs. We have a finite time horizon problem, say 24 hours. And then subject to the net load, which is this duct that I drew before, being equal to generation plus this virtual, generation from the loads. And maybe the batteries could be thrown in as well. Okay? So again, if UI is positive, it means I'm consuming less energy than nominal. Okay. And again, the goal is to make this flat. And I wish I had given a plot. We've done estimates, like just with the current loads in California, we can make this pretty flat. All right. And then, that's a typo. But the point is that the fact that from this algebraic constraint, you can eliminate G and just get a control problem in terms of the X's and the sum of the UIs. Right? It's a singular optimal control problem. And so you're going to get some sort of collapse. And so that's a well-known fact. Right? It's extremely pretty in this case. You get a really, really simple problem. So you could have, what I'm going to show you is you could have 1 million load classes, and you end up with a 2-dimensional optimal control problem. 1 billion, it's 2 dimensions. Doesn't matter what. It's always 2 dimensions, this optimal control problem. That's what we'll see. Okay. Now, so again, state space collapse, there was this, I mean, it's still going on, but it was incredibly active in the 90s and up to 2010 or so. And I just picked out some some seminal papers here. And you see there Frank Kelly and Not Laws. That was a favorite of mine back then. But the whole thing was about taking a complex queuing network and justifying a low-dimensional approximate model. All these papers looked at a one-dimensional relaxation. So it was a collapse of, say, 100-dimensional optimal control problem to just dimension 1. And I ended up writing an entire book on this. I was obsessed with this idea that you could take a complex scheduling problem and project it down to 2 dimensions, and then solve the 2-dimensional problem and map it back up. So that was just, I was, very much involved in this. So you'd think that since I loved this so much, I was looking for state space collapse in power systems. That's not true, I swear to God. Joel was trying to, solve this problem, and he played around with it, and he pointed this out. So I wasn't looking for this. Didn't have a hammer looking for a nail. It just happened. Okay, so let's just do it. So let's go and solve this problem. Just in time. We're just about to solve this optimal control problem. And I'm not using deep MPC, but next time I will. DPC. What is a deep C? Okay. Yeah. You two actually are just in time, because this is just, you didn't miss anything, because you've seen the other stuff.
Minimize what G and U.
So yeah, so we have an optimal control problem with the most boring linear dynamics, and but subject to an algebraic constraint. And I was just saying that I've got a G here, a derivative of G here. From this algebraic constraint, I can eliminate G, just substitute this in, and I end up getting a cost. I mean, I replace the G's, get rid of G's and have UIs in here, and then I've got the UIs appear here in the dynamics. And because I have a sum of cost, it's the reason I get a simple problem.
John, can you repeat again what I use in X?
Yeah, well, okay, so so this is the average. It's a normalization of average temperature of the population if it's water heaters or refrigeration or something like that. Yeah, let's just stick to TCL. So it's the average. It's a normalized average temperature, and we want to stay in some bounds, normalized so it's plus or minus C, say, and if it's minus U is a normalized power consumption, and the reason for the minus sign again is because I want the units to be right.
But that's average again, no?
Yes, everything's average, but we have lots of papers to justify that. Even it seems really funky looking at the average temperature of the population. Seems like not nearly enough information, but we've done a lot of. It's all empirical, but we have a million papers where we studied capacity, and we've shown we can almost achieve what this, the constraints that are imposed. We pose constraints on this instead of a convex cost function, and show that as long as the reference signal didn't make us violate the constraints, we could track it. All right.
So Sean, what's calligraphic L? What's L?
Yeah. Oh, yeah. L was that duck. L was the net load. So we want so what we're trying to do. Yeah. So it would have been much more intuitive in a way to put that sum of UIs on the left-hand side and say that's the new net load. We're trying to make the net load such that G is basically constant. That's what we'd like. All right. So what you do, anybody looking at this would say, oh, relax the constraint, this is just so standard in control, especially in the last, everyone loves Lagrange multipliers, and, basically, almost always for this reason, because you have a constraint like we had, that this is 0, and you put in a Lagrange multiplier, and it becomes separable, and it becomes very easy to solve. Okay.
I'm sorry.
Yeah.
I subscript for 1.
Oh, yeah. So there's like 5 loads. I've got 1 million water heaters, 1 million commercial water heaters, 1 million commercial refrigeration units, a million residential refrigerators.
So your sigma
Yeah.
is the sum of all.
Oh no, it stayed there. Ah,
So it's
I forgot. Oh, I thought I got rid of it. Sorry. Yeah. I meant to get rid of the sigma. It's in the paper, but I meant to get rid of it in the talk. If there are any more sigmas around there, it means a sum. Sorry, I meant to get rid of those.
No, but
The first time I
those
presented this
are
material.
loads. That's not the.
The UI is the average, well, minus UI is the average power consumption for that class I of loads.
So why do we have sigma then?
Oh, no, right there, there's a sum.
Yeah, why do we have sum?
Oh, yeah, no, because I want the sum of all the power contributions from all the loads plus the generation to be the net load.
From the what? Fridges, the heaters from the different groups.
I'm summing all the different loads, load classes. This is a sum of the load classes.
Okay.
Okay? Yeah, sorry about that. I've got to make a note of that. Okay, so this has a beautiful solution. So let's go solve it. So basically we've got, we look at this Lagrangian here. It's separable, and we're going to optimize over G, and we're going to optimize over each xi. And so if you look at the grid operator, the grid operators, that says grid, it should be generator. The generator is optimal control problem. Generator, let's assume it's Florida, and the grid operator owns the generation. Okay. The Lagrangian looks like this. And when you go through and you look at the Euler-Lagrange equation, which we all know and love, and you take the derivative with respect to G, you can see what that is. And you can take the derivative with respect to G dot, you can see what that is. And whammo, you get this pretty equation, okay?
I guess I'm the only slow one.
Yeah,
Why
no.
G dot?
What's that?
Why do you have derivative?
Oh, because I want to impose ramping costs. Because I'm trying to flatten the duck. And so I want the net load to be flat. And so in order to do that, I want to put in a derivative cost. Nobody knows what that cost should be, but we know there's a cost. Our real thing is we want to get rid of peaks because we don't want, we want it flat for other reasons besides there really being a derivative cost. I mean, it's a good question. We don't really know what the ramping costs are for generation, but we sure know why the generation should be flat. I mean, we all know that. We don't want a peak of 10 gigawatts for 5 minutes or whatever. We don't want that. We can't, it's infeasible. And it also means that you've got somebody doing nothing except for 5 minutes. So. What's that? What's that? Well, yeah, the thing is that we don't know the physical meaning of the cost of ramping is what I'm trying to say. There's a cost modeling question here for generation, just like there is for batteries. There's a lot of uncertainty about what the costs are in operating a generator or a battery. So this is a heuristic really to get a flat response. Okay, so you get this pretty differential equation. All right. And then when you do the same thing for loads, the Lagrangian now looks like this. Is the cost of generation. I mean, this is just what we got from that relaxation. And again, I'm just writing down the same Lagrange equation, writing xi's instead of g. And you just plug this in, and you take the derivative with respect to xi over there, xi dot. It only appears there, so you just get a row. And whammo. Oh, that's right. Yeah, the Euler-Lagrange equation has a minus sign. Yeah. Again, it's the first time I give this talk. I'm terrified of typos. But okay. So anyway, so you get these pretty equations, and then I'll explain to you what state space collapse is. I'll just show you what it means, even though it was right there. So let's assume this was my Lagrange relaxation. This is a dual functional, so it's a function of the Lagrange multiplier rho. Assume it actually has a maximum. So the dual problem is to maximize this over all functions. And assume it has a C1 maximizer. So I need to assume it's differentiable. So you'll need conditions on the cost functions. And then you get the state space collapse. And it's just so cute. I mean, basically, again, there could be a million loads, but to get the marginal cost for the ith class of loads, it's equal to minus alpha high times this Lagrange multiplier, where alpha was a parameter in the dynamics of the state of charge evolution, and then the derivative of this Lagrange multiplier. That's it. So the marginal costs evolve in a two-dimensional subspace. And you can identify, it's plus 1 and minus alpha I, the marginal costs. All right, so let's look at this. Just take this example here, where we take this curve here. And I just want to show you what this looks like, because it's really fun to play around with. And this, again, the 5 classes of loads, and it really, the details don't matter. So here's an example. So suppose I knew the optimal state of charge evolution for the air conditioning and for the pool pumps, all right? And I could go through then and write down a formula for the Lagrange multipliers. So if you told me the optimal solutions for just 2 classes of loads, I have just a matrix inverse, and it gives me, from the optimal trajectories of these 2 classes of loads, I get the Lagrange multipliers. Then obviously I can go through and find any other optimal trajectory. And here's an example. So I know the ACs, I know the pools, and I can take a mapping, and I get the residential water heaters. That's it. It's cute, right? Is it useful? I don't know, but it's really cute. And so, don't tell me now. I'm sure that other people have done exactly this already. So I know I'm going to be told it's not new, but don't tell me now. Okay. So anyway, so it's pretty. I mean, this is actually, just repeating it, working out numerically or inverting, you get the same answer. Okay. Now let's get into some politics. So this is a joke from January. It's just this is this guy. I don't know who he is, and a co-author in Kucho at Illinois, and just the two of us, had a bunch of papers on pretending that consumers had a utility for power, and I was just making fun of us because it was a silly thing to do in the first place. But so you could think of what we've done is the social planners problem, getting ready for a market analysis. And you'd say there are n+1 players, generation in the different consumer classes with their decisions, minus UI. You'd have to expand this out if you had 10 generators, because it's a strictly convex function, and a convex function of a sum of the sum of convex functions of generation is not the convex function of the sum. So, we'd have to, if you want 20 generators, you're going to have a n+20 players, right? That won't change the results at all. And the social planners problem, again, is to maximize the sum of the social welfares for the 2 players, subject to physics, that what's going in is coming out. There's physics here, so that would be there. And then you've got these utility functions without prices of the 2 agents, as I've described before, right? And a dynamic competitive equilibrium is where the generator, you have a price process. So when the generator maximizes and the utilities maximize, you get the same outcome. There's an algebraic constraint. So once you know the UIs, you know the G star. If you know G star, you know the UIs through other things. But if you just go back and backtrack where the calculations I've done, all we did was compute this equilibrium price. That's all that was done in this calculation. Okay. Apparently, well, yeah. So first of all, I didn't know this until a month before submission that Nali and Stephen Lowe actually had a paper looking at this problem with not classes of loads, but discrete, variable loads that could be variably ramped up and down, and had prices, not the state space collapse prices, and apparently James and Stan have been working on this as well. So I just learned that from James's talk. Okay, so anyway, so basically this rho star is the competitive equilibrium price. And if everybody was doing this, then this would be a competitive equilibrium. But don't forget, this is for the population of loads. So there'd be an aggregator. You'd have to have an aggregator. You can't be with the individuals. They're on-off loads. There's no convexity. There's no competitive equilibrium theory for these on-off loads. There's no way you're going to do that. So you're going to have an aggregator in place, and in principle, with these prices, the aggregators would all act in optimal fashion, right? Okay, and so the thing that I thought was fascinating back within Couchot a million years ago was that average price was approximately average marginal cost. Well, you get something similar here. If you go back to the, so basically look at the average price, the average marginal cost of generation, and the average marginal value for a consumer, you just take the negative of the cost and average it, marginal cost and average it. So in a purely static problem, price would be marginal, value would be marginal cost. That's not true here. So you go back to the Euler-Lagrange equations though, and you see here that price is like marginal cost of generation plus a derivative, you know. And here you have this weird thing that price, I could put a minus sign over there, it's like marginal value, but there's an alpha that you'd have to divide through by. That's really funky. You know, so this isn't too bad. That's bizarre. You know, I don't see any way that's related to marginal value. I don't get it. But if you integrate it, you know, it's a little better. So the average price, well, down here, the average price is the average marginal cost. Just integrate both sides of this equation. When you integrate this, you use a fundamental theorem of calculus, right? Remember that? And so you'll get the difference of the endpoints divided by t. And if it's 24 hours, you imagine the prices probably aren't that different. And you divide it by a big number t. And so this, you know, that's probably not too big compared to t. This is weird. I mean, you get the average marginal value divided by its dynamic parameter. What the? Oh, we need an economist to explain this to us. I don't, I don't know. But somehow, yeah, somehow that's average marginal value. I don't know. So let's, to be discussed. All right. All right. So let's look at this real fast. I've got lots of time, right? And you're all still awake. So here's something intriguing that you really might get excited about. So take the duck curve and look at the optimal power deviations for the loads over this 24-hour period. And this does pretty much flatten the net load pretty well. And here's the net load, that thing that I showed before. That's the duck. And that price, check it out. I mean, it's like everything I said's a joke. It does work. I mean, it's just what anybody would have predicted. You know, I've got my net load. When it's high, the price goes up. When it's down, the price goes down. Price of devices, I take it back. I'm sorry. So if you look at this, you think, my God, it's all solved, because the price you get from solving these Euler-Lagrange equations is exactly what everyone always said it should be. All right. So let's check this for its generality. Suppose you had the standard thing that people talk about in California up until recently, or in New York for sure forever, is that there's a 2-hour period, 90 minutes, I need a load reduction because I don't want to turn that peaker on. And in New York State, they've been trying to deal with this forever. That there's like just an hour and a half every day where the power is too high and they don't know what to do about it. We know what to do about it as control engineers, but they don't. And so based on that prior plot, that the price and the net load look the same, the thing you're trying to track in a way. If you had a net load that looked like that, you'd predict the price would be like that, which would be consistent with what anybody would say you have to do. You know? But you know what it really looks like is a sine wave. Isn't that wild? Can you imagine that that is the optimal price that would result in that behavior from the loads? And the generation becomes exactly constant instead of having to go up and down like that. And but the only way to achieve that is with a sort of sinusoidal price. Who would have guessed that?
To do with your ramp rates, that it's much smoother to do that than the other in terms of the price?
There is a derivative in those equations. So if it's something very, very smooth, then you're going to get, then you're going to get, they'll be more similar for sure. But yeah, I mean, but those, yeah, I mean, yeah. Anyway, I can't give you any general statements. Yeah. So I just want to go back and, 10% of you were here in January, but let me go through what actually happens when you optimize with the standard price that people think about. So this, people always propose that price to try to incentivize behavior, and it's wrong, And most of you, I know you've seen this, but sorry. And I've flipped things around here because this is taken from January's talk. I didn't get a chance to redo these slides, but I've got a period of 90 minutes when I want load curtailment by some percentage. And this is actually the statistics for those previous simulations. That I've got a bunch of ACs, water heaters, commercial water heaters, and so forth. And I've got aggregators who are promising strict quality service bounds to each consumer. And if you end up looking at the resulting quality of state of charge evolution, it will be nice. That's what I mean. There's some bounds here for state of charge for each of the loads, and they're all within bounds. And if you do the standard thing, which is to put in a 10% increase in price during this 90-minute interval, and then solve the optimal control problem that I described at the beginning of the talk. So there's an event here where I increase the price by 10%. Again, I want load to decrease during this interval, just like before. And this is what's going to happen. I mean, these ACs are going to pre-cool, and so they're going to consume a ton of power just before the event. And all these loads are going to pre-cool. Why wouldn't they if they're told in advance? Now, if you withhold information, that's even worse. If you don't even tell them, why would you withhold information? There's no way. This is time of use pricing, and I will debate anyone who thinks that it's better to have real-time prices, withhold all the information, and so they say, price is up. Didn't give them a chance to prepare? I mean, why would you do that? In engineering grounds, it's idiotic not to let them prepare. Anyway, so the ACs can't turn off very long, so they go back up. And sum these all up, and you get this spike up from 5 gigawatts to 15, it drops to 0. 0. You didn't want 0. You wanted a 10% reduction. And then it climbs back up, and there's a rebound. Now, the rebound people talk about all the time. But if everybody had a Nest thermostat, and you had a price like that, this is what will happen, because it's the optimal response. This is optimal. This price is ridiculous. It doesn't make sense. And the pre-bound is way worse than the rebound. Okay? All right. So that's that. All right. Is that clear? Yeah.
Do you need non-causal access to the L?
Well, no, I'm just saying that's reasonable. I mean, whatever information the balancing authority has, they should share. It really, it just doesn't make sense. We can debate that, but if we really care about the grid, and it's a public good that we all care about, why would anyone withhold information that's critical? There's a bad event happening at 2 p.m. Everyone should know. It's crazy to think you should withhold information. So if price signals for control made sense, then they should be broadcast in advance. But they don't make sense for a lot of reasons, which in my remaining time I'll try to say a few words about. I have a million reasons why, but okay, so any other questions? Okay. So in conclusion, proposal, there's this notion of value of lost load. I propose that that's as silly as Sean Meyn and Inku Cho 15 years ago. How about the value of lost QoS? And that's a metric for performance that makes a lot more sense. And then we could have a serious discussion about how much QoS can we afford to lose, or do we need to lose anything? We can shed 30% of the load for 2 hours and nobody feels a thing. So this, I think, is a term that would be much more valuable and less silly than deep PC, by the way. No, but just that value of lost load never made any sense. And it's used for pricing rules. I mean, Bill Hogan says that you should take the value of lost load, multiply it by the probability of blackout, and that should be the price. You're multiplying two meaningless objects. Meaningless doesn't make any sense, is not defined, and probability of blackout, not defined. So in Texas and New York ISO, they're trying to implement that pricing scheme. You multiply value of lost load and probability of blackout, you get a price. It's amazing. So anyway, that's a proposal. But I want to say, rho star is not a price. It is a Lagrange multiplier as part of a control solution, It's computed based on forecasts of renewable generation that might be terrible, and energy needs over the day, and it's going to be part of an MPC control architecture. If you tried to force this to be a price, you'd have to update it every 15 minutes. The price would suddenly jump up. People would have to shuffle around. The individuals wouldn't notice it. But what would you gain? Why would you try to introduce the uncertainty of the behavior, of the response of the aggregators, when we have a beautiful control solution? The aggregators, who knows the genius of the market? The aggregators might come up with some wild ways to mess around and be irrational temporarily to put everybody out of business. Who knows what would happen? We have a control solution that can flatten things out. It's efficient in the strictest sense of the word. And, there's no way this is a price. Calling this as a price is completely superficial. I hope the economists agree with me. If not, I don't understand. Anyway, I don't believe in high-frequency trading either, but that's another story. That might be valuable, I don't know. But this high-frequency trading doesn't make sense as a control solution. We don't have real-time markets for ailerons on planes. And we don't have real-time markets for congestion control on this, And apparently there were debates on doing that, having price surges to try to get people to use less bandwidth. And TCP came along, and that debate ended. In the early 80s, they talked about real-time prices for bandwidth, and then distributed control said, gone, all right? And I think the same thing should happen here. Markets are beautiful on certain time scales for certain uses. So what's exciting to me is just the fact you get this wonderful model reduction. You get a two-dimensional optimization problem, even if there's 10,000 load classes. Okay, back to the homework assignment I gave in January. History, how did we get here? Fred Schweppe was not that dogmatic. He talked about the issue of sunk cost. He said that spot prices probably isn't going to do it. And yet, people only quote the most extreme things he said in his book. He was very measured. And so, in no other field are you forced to justify your control solution by saying you're going to incentivize customers through spot prices. So I don't see any economic justification for this real-time trading. I don't see it. And fixed cost, now we're always saying fixed cost is such a big deal because of renewable generation. It was always a big deal. It's something like the variable cost for natural gas generators, these efficient generators, is like 30% of the cost of the lifetime of the unit. There's staff, there's incredible, it's $1 billion, It's $1 billion you stick down, you're stuck with that investment for 40 years, all right? So why are there no people from industrial economics here, ever? I've never met anybody from industrial economics whose whole work is about dealing with fixed cost. I mean, I've never met one. I've never met, are you? Really? Are you really? Well, why do we talk more? Damn it. I mean, really, we were sitting there having sherry for an hour, but there's never but why don't these issues of friction ever come up? It's like, this is blasphemy. So, from my experience, I moved to Florida 7 years ago. I feel like the dictatorship model works really well. You drive down to the Florida Keys, you see that beautiful infrastructure. No hurricane can knock those things over. The prices are the lowest in the country. Basically, when hurricanes do knock over power lines, they pop back up in 3 days. You've got this value when you have a complicated industry where you need a lot of expertise, and when sunk costs are 70% of your total cost, there is theory to say that you shouldn't just think about marginal cost theory. There's a claim, people always make fun of vertically integrated utilities. I think that is completely arrogant. All right? I don't think I'm arrogant. I think saying that is stupid is arrogant. I'm not saying I have the solution, because FP&L is corrupt too. I mean, because they've got deals with the governor. There's political issues as well. So no system is perfect. They all have flaws. But we do need a foundation for zero marginal cost resources. And before it was only 30%. It wasn't zero, it was very low. Natural gas, coal, they're cheap. So we need some sort of economic theory, and David, you should be leading the way. And we need a CEO model because, again, whether it's a wind generation plant or natural gas, you've got that asset, you're stuck with it for 20, 30, 40 years. There's risk, which is massive. Has anyone met a risk-neutral player? They don't exist. Risk is everything here. And I'm not an economist at all, but I know enough, to see this. So back to that joke I made in the beginning. It's amazing when these slow timescales, the difference between congestion control on the internet and congestion control and power seems so small. It's amazing. I think the biggest challenge is variability in timescales of days. If there's no sun or wind for days, that's something you don't see in telecommunications. And that means a change in lifestyle. But if we just want to get 50% renewables, I think it's just like telecommunications. And when we look at distribution along with transmission, I used to think, I've always put that up on slides, is like something I'd like to do someday. And I'm finally doing it with this company in Austin. So I think there might be more value than I originally thought. But a thank you. That's what my house looked like the day after the Hurricane Irma. And like I said, all the power lines just were cracked off. 5 days later, all brand new and beautiful. So, it is amazing. And this is my final quiz question: is which one of these is a Stalinist dictatorship? I asked this in January. So Coase, has a memoir where he talks about exactly the kinds of things I'm talking about. He says, why do people believe in these frictionless markets and that you can just do everything with marginal cost? And he says that, you could justify it if you could change your assets instantaneously, but you can't. And he says, why is it that every one of these companies is a dictatorship? There's a CEO who's a Stalinist. If you don't do what he says, or she, you're gone. You walk out humiliated. It's a dictatorship. And you can tell us why. It's because Coase explained it in his memoir beautifully. You need to have these vertically integrated, you need the brains to stay around for a long time. You're going to buy an airplane, you're stuck with it for 30, 40, 50 years. You need long-term planning. Every one of these companies is a mini dictatorship. It's not the wild, wild west. Power is the only area I can think of where you have to debundle, and not let them have the efficiency of these big companies. And FP&L is very efficient because they can make long-term planning decisions. It's not perfect. I know the flaws. I can give you them, but so there. Anyway, I hope that could start a debate. Continue a debate. I hope to start this in January. All right.
Thanks, Sean, very much. So we have a few minutes for some questions.
I have two reactions. One is, and I'm not a mathematician, but a long time ago, there was this great idea that duality in economics meant instead of talking about large numbers of individual consumers, each with their little consumption bundle, you could say there's a price which separates.
Yes.
And work in terms of indirect utility functions. And you could transform multi-dimensional problem into, if it was just one group, a single problem. So I don't know if that's the same thing here.
Oh, I don't know.
Separating hyperplanes and stuff like that.
I'm not sure.
Aggregating all the loads, I suppose.
Yeah, maybe. It's possible. I'm not sure.
It just comes out of convexity.
Yeah. Well, here it's a very special thing. It's that we're looking at.
Anyway, that's sort of an aside.
Yeah. Okay.
And it hugely simplified an awful lot of economic analysis, and it meant you could, because one of the huge advantages is you can't easily observe the individual consumptions of large numbers of consumers, but you can observe the price.
Yeah.
So you can do a lot of econometrics on the prices.
And
infer that.
Yeah.
The second question is, you're hostile to prices, but what's the signal that you send out?
Oh my God, it's right there. You know, I mean, that's what. So the thing is, it's just like here. You know, there's congestion control in here, and you know, there's pings that come in, and it ramps up and down the rate. I mean, so. Well, actually, Anna gave a survey of one possible technique yesterday, where the
at a purely practical level, you've got all these pool pumps or whatever it is.
Yeah.
What is it that is causing them to do what you want?
Yeah. So here's one architecture that I love. Is that basically every you know, you take where is it with LFT, you broadcast LFT to all of the loads in your region. All the water heaters, all the pools, they each have a little chip, and they solve this little program, and they flip a coin, and they change their power mode based on LFT, their current state, and we've got 1,000 papers now.
So it isn't just the frequency.
No. You have to. So there'll be. Yes. Oh my God. Because there's too much information beyond frequency. There's tie line errors. There's forecasts of wind and all that stuff. So you broadcast this to all the loads, and then they do the little computations and flip a coin. And it's quite similar to, you know, to what computers are doing today with for congestion control. You know.
So Sean, your row star, you say, is not a price.
It's not. Yeah.
But it looks like a price.
Yeah, it looks like, that's the thing, it's superficial. The reason I say it's superficial, it's like what I was saying earlier. These things are so contrived. There's no quadratic cost of generation. We stuck that in because we want to make it flat. And we don't know what the cost is. You know, it's really, really subtle. There's so many things that, and also this was all based on forecasts. We're going to repeat these forecasts every 5 minutes. So if it would, this price, you're telling somebody the price for the next 24 hours, or you know, it comes from God or whatever, it's going to change dramatically every 5 minutes. You know, it's just nothing like a price. You know, in the sense of there's no Aero-Debreu theory here. There's no auction theory that would support this. You know what I mean? It only has a superficial nature of a.
It's a long-term contract. You do your TCP signal, or you do your pricing.
Yeah.
If you agree that you will pay by these rules of the,
Well, that's
the game.
yeah.
There's a sort of long-term implicit market mechanism there.
Yeah. Well, it could be part of a payment mechanism, but again, it's based on a completely contrived notion of cost for the generator. You know, it's really.
So you had an equation earlier on relating rho star and rho dashed star. The one where you commented, what's alpha? Oh, that was it.
Oh yeah, it fascinates me.
Yeah, so, but alpha is kind of like if one of the storage devices loses some, X goes down.
Yeah, it's leakage. Yeah.
The leakage is a cost to it.
Yeah.
The value of it is the price at that time.
Yeah.
Energy.
Yeah.
And it's changing its derivative by doing that. So there is a way of relating the alpha to the equations, isn't there?
Yeah, maybe so, yeah. It's weird that alpha equals 1 would make it, a leakage of 1 would make it marginal value. But yeah, I have to think about the units.
No, it's 1 minus the leakage, isn't it?
What's x dot equals minus?
1 minus, yes.
It's x dot equals minus alpha I.
Yeah, the leakage is minus 1 minus alpha.
Yeah. I mean, this is the survival.
Yeah. I'll have to think about it. Yeah. No.
Sean, so you were asking like, what does one gain by making rho the price? Right? So the only thing, I guess, the thing that you are losing is the autonomy of the load.
Yeah. I mean, the loads, like I said about the water heaters, nobody cares about those spike trains. If you can't even see the difference between those two plots. I'm not cheating. Those really are different simulations.
My actual question is, suppose you put in also a QoS constraint in your social welfare maximization problem.
Yeah.
So how would things change?
Oh, yeah. I mean, so basically everything would change. So we're taking, so this all falls apart. And that may be, I mean, if we used hard constraints instead of convex functions, it would fall apart, you know. Because as soon as, you get different state space collapses depending on who's at the boundaries. You get a sequence of state space collapses. So I'm just saying we're going to take something which is practically 0 and blows up like x to the 100 or something. I mean,
But presumably there's a natural model of an aggregator with controlling loads, where even if the individual ones have features like that, the aggregate of them, well controlled by the aggregator, will have a convex cost. Even if the individuals are far from convex, if you've got enough of them, just randomization across the alternatives for convex.
Yeah, sure. I just meant that if I put in hard constraints in this problem, it would not be so pretty. But it sure seems reasonable to me to put in a convex cost, especially since these individuals do go out of bounds occasionally anyway. I mean, it's not like they really are hard. They never were hard constraints to begin with. You know, a shower does go out of bounds today. So,
doesn't it indicate a kind of architecture which is potentially one that works? These psi signals have to be sent out, right? They're quite complicated to work out, and someone has to work them out. The end systems have to react to them. So it looks like Nest or someone.
Oh, that's, I should have said that, absolutely.
And then at the level of Nest, it does look like a convex cost. It's doing a lot.
Yes. And that's right. And this is meant to be a resource allocation problem. You know, this is related to a signal that's sent to the ACs and a signal that's sent to the water heaters and to the pools and so forth. And so so for the aggregator's point of view, everything's beautiful and convex. An individual, it's a combinatorial nightmare.
But the aggregator could be potentially charged a price, because the aggregator is smart enough to be able to handle prices for both ramping and level.
But if they were being controlled through a price signal, we'd be introducing uncertainty in their response. You know, and we wanted, the more accurately you track, the more valuable the service. You know, and so introducing uncertainty of response is very costly. You know, so the prices would be a dangerous thing to do.
But you're assuming that there is no cost to varying the load.
Oh no, I'm not saying we shouldn't compensate. Maybe.
No, I mean, that a short-term adjustment is no more costly than telling people 5 hours ahead. Because you want to be able to continuously adjust it in real time. And how often you do it is irrelevant to the cost of the whole system. The usual objection to not having enough warning is it is actually more costly to do things quickly.
I mean, it's costly to not have warning because you want to preheat or pre-cool. You want to charge or discharge your resources. I'm not sure I understand the point.
If I might just say, so we have a panel session coming up shortly. I know there are more questions in the room, and so let's continue this discussion. But could we just, in a moment, show our appreciation? The administrative staff are going to come in. And if your experience has been anything like mine, they've been absolutely fantastic. So let's just invite them in, and once they're in, we'll give them a round of applause, and then we can move on to the
So shall